people across disciplines. So a few motivating comments at the beginning about just data and policy issues around data. Of course, data is useful for all sorts of things. Nobody would be at this conference if you didn't believe that. But there's also, data isn't free to collect and use. One area of concern about collecting data is just, the retention of data, and that creates risks to privacy and security. So, if nobody's kept your data, it can't be breached. And longer data retention will compromise user privacy more as a more complete profile is built. So, even, I've been working in digital commerce and search and things for a long time. And, 15 years ago, I felt like, well, yes, you don't have to worry about the data, but what's really the consequence if somebody gets your data because, you've been to a few websites, like what difference does that make? But today, when you're being potentially tracked across all sorts of different places, your mobile device is keeping track of where you go, and all of that information, while it could have been pieced together in the past, in practice, people weren't piecing it together. Now it can be pieced together, and some companies, especially companies that see you on the web and on mobile and doing search queries and other things, are piecing it all together. It can be much more risky. And so one question you have is, are there quantifiable efficiency benefits to retention that outweigh the risks? And then a second issue that comes up a lot around data and value of data is just that data can be a source of competitive advantage. So first of all, firms need to think about that when they're thinking about strategy. If you're thinking about entering a new market, maybe that's partly valuable just for the data that it brings. If you're thinking about coming in and competing with a bigger firm, you might worry whether lack of data puts you at a disadvantage. And you might also make decisions about buying data if there's data that's useful that can be bought and sold. So policymakers have been, focusing on data as a barrier to entry, and especially in this current era where there's a lot of tech regulation, this issue comes up. But of course, part of the problem is that, this is an empirical question, and different types of data may have different returns. So there might be some types of problems where you can get started with a small user base and a small amount of data and do pretty well. And there may be other kinds of problems where even having a whole lot of data isn't enough to solve your problem. And there are bigger picture questions about that in the settings where you need a lot of data to make progress, also about the distinction between universities and companies. If you need lots of compute and lots of data to even get started on a problem, then we may see a lot of that research taking place inside of companies instead of in universities. And that might change the direction of research. And we might also have implications for society about the things that the firms aren't incentivized to do. So those are some questions that we think about a lot at the Stanford Institute for Human-Centered Artificial Intelligence. When we think about the value of data in a more technical way, we can actually realize, if we think about it for a few minutes, that there are potentially lots of different possibilities for the value of data. And so I've put here in this picture, like on the y-axis, in some cases, you might just be interested in goodness of fit if you're trying to do prediction or classification. But if you're trying to use, say, targeted treatment assignment policies, like giving the right offer to the right person, the right recommendation to the right person, setting, giving targeted discounts, things like that, then you would be thinking about the incremental profit from having more, or the incremental utility you provide from having better recommendations. And there's lots of different shapes that are possible. Part of the shapes of these curves, of course, depend on the underlying structure of the problem. How complex is it really? If there's only two things that you care about, about a product, then it may not be that hard to learn your preferences about those two things. While if your preferences are very complex, you may need more data and also more observations on individuals to learn those complex preferences. And another type of question is, do you therefore need to grow the complexity of your model as the data set grows? So, in the simplest case, if you're trying to estimate a mean of a variable, then, the quality of your estimate goes down, goes up, roughly proportional to the square root of n. And that's, just simple statistics. But if you are instead making your model richer and richer and adding more and more parameters as you add data, then you might hit diminishing returns much later. And in principle, you can even have some kind of an S-curve where you need a certain amount of data to really get started making sense of a problem. And so this then becomes an empirical question. So in the talk today, I'm going to give a couple of case studies where these where you may be able to make progress with little data, or in some cases you might need a lot of data to make progress. Now, to another important consideration in thinking about the value of data and whether data is useful is the question of prediction versus causal inference. So historically, a big chunk of machine learning and computer vision and so on were solving, these problems of prediction and classification. Can I use X to predict or classify Y? And then, we can, something like risk scores or click prediction or, image classification. And for those kinds of questions, it's, relatively straightforward to say, oh, if I've got all this data, that data is going to be useful for this prediction. Like, how many examples do I have is sort of the main thing I have to think about. Now, there's some things like maybe the environment is changing. And so then you need to think about how many observations do I have relative to the rate of change of my environment. But roughly, like, you can kind of count examples and start to get a pretty good idea of what's going on. For targeted treatment assignment, I'm asking questions like, what is the difference in counterfactual outcomes if I assign an individual to A versus B? That's the question you need to answer if I want to make a decision about, should I give you A or should I give you B? And so there's some additional considerations that come up when understanding the value of data for those questions. So the first part is just separating, correlation from causality, or, prediction versus causal inference. And so basically, just in order to answer the question of, is A better or B better for a person with whatever characteristics you observe about that person, you need some kind of variation in the past. Like, if people like me have only seen A in the past, I have no idea what would happen if you showed me B, right? So you need to have somehow had people like me, or people with histories like mine, or me as an individual, have to have been exposed to A and B in the past. Now, the second thing is, well, why was I exposed to A versus B in the past? Was it a randomized experiment? Maybe the company was experimenting, or maybe the government was experimenting, but somebody may have been truly running a randomized experiment. And that is going to make the data a little bit easier to analyze, because I would understand that, the reason I saw A versus B was not related to anything special, unobservable about me, but it was random. On the other hand, if there's some other reason that I got A versus B, then you have to think about why I got A versus B in order to know whether it's possible to estimate the benefits of A versus B. If you thought about, just imagine you're a student and you can sign up for the teacher who uses a flipped classroom and the teacher who goes in person. If the student gets to choose the flipped classroom versus in person based on their own learning styles, then if I compare outcomes for the flipped classroom with the in-person, that's not going to tell me about what would happen if I took the people who chose the flipped classroom and put them in an in-person class. The fact is that the people who chose the flipped classroom would be different than the people who chose in person. So you have to understand why, and you need some kind of variation that in the data. Now we talk about quasi-experimental variation. That could be something like, maybe you were only eligible to do the online class if you met certain criteria. And for example, there might be some people who were just over the criteria and other people who were just under the criteria. And so maybe we could compare those people, and we would call that quasi-experimental variation, because we might think it's random whether or not you cross the threshold. And in economics, we have a whole set of scenarios, if you like, or designs, we call them, for quasi-experimental variation that commonly occur in practice and that we often use to try to learn about treatment effects. In a company, it might be something as simple as like, you live in one place versus another, and the latest version of the app got updated on one server versus another, but otherwise the locations are similar. You might compare people before and after. Like if you flip over at 2 p.m., you compare the people who came between 1 and 2 to the people who came in between 2 and 3. So there are lots of types of quasi-experimental variation that occur in practice, and that can be potentially exploited. But you have to look for that and understand it. Otherwise, you won't be able to infer anything about causality. Then second, you need to if you're going to try to do something personalized, you need to customize your machine learning optimization for estimating causal effects as well as counterfactuals of interest. And this is because, it's very common that it's pretty easy to predict your overall outcomes. Like if I had your last year's test scores, that'll predict this year's test scores pretty well. But if I want to predict whether you'll do better in an in-person class or an online class, that might be much harder to tell. And it might be very different characteristics of a person to which modality of instruction works better for them. And so it's going to be important in an environment with somewhat scarce data that you optimize for heterogeneous treatment effects rather than optimize just for predicting. Predicting is the easy problem. Finding out who likes what and based on characteristics is a hard problem. And that leads me to my second point. One of the real challenges in causal inference is statistical power. You might have piles and piles of historical observational data, but in that observational data, there wasn't enough variation in treatment assignment for you to actually learn the difference in outcomes for certain people between treatment A and treatment B. So the historical observational data just may not be that useful for you. And then what you may be stuck with is a much smaller experiment where things are noisy. The second thing is that in most settings, treatment effect sizes are small. Like sometimes you have a great idea and it's really effective, like vaccines are really effective at preventing hospitalization from COVID. So you got a nice big treatment effect. But most of the time, if you're trying to improve a product or a service, firms are already doing pretty reasonable things. The prices they set were already pretty reasonable. And so it's actually pretty hard to find treatment effects, even overall, but especially if I'm trying to do personalization. Personalization is hard. There's never enough data. There's nobody just like you. And there's not enough people just like you to be able to learn from those nearby people. So there's fundamentally, you generally don't have enough data to do targeted treatment assignment, even in large production systems. And so those are like some of the big challenges that you face, and why, in some sense, causal inference for personalization is always hard, even for big companies with big data sets, but let alone small companies. So now let me talk about a couple of applications that sort of illustrate some of these ideas about statistical power and also prediction versus causal inference and personalization. And I should say all the work I'm going to present today is in progress. And so I guess I always like to talk about the latest and greatest rather than the old news. So apologies for some things being a little bit preliminary today. One is a recent paper that we've put out that was going to analyze an experiment that was run to try to get students to apply for financial aid. So FAFSA is an abbreviation for the Federal Financial Aid Program in the United States. And the United States is sort of notorious for putting a lot of red tape and bureaucracy for people to get benefits, and this is no exception. It's really onerous and difficult to apply for financial aid for college. And City University of New York, or CUNY, is a system of higher education in New York that predominantly serves first-generation college students, people whose parents did not go past high school. And so we're trying to help them apply for financial aid for which they're eligible. And so what the experiment that was run was that some people got a sequence of text messages that helped remind them and give them information about deadlines for applying for financial aid. And we call those nudges because they're sort of they're low cost, they're text messages, but they're trying to put people over the hurdle of applying. And so our questions are, for whom are nudges most effective, and how well do targeting approaches work in practice? So this was an experiment. The actual original experiment was run in 2017 and 2018 by a nonprofit called Ideas 42 in the City University of New York. The control group got business as usual emails from the college, while the treatment groups got supplementary behavioral emails and text messages. The people in the study were matriculated students from these colleges who had not yet renewed their financial aid in February of the study year. So you have to apply for this every year. In 2017, we had 25,000 students, and in 2018, we had 40,000 students. So this is sort of small by the standards of, you know, a search engine or a social media network, but this is big by the standards of, you know, experiments on humans run in a social impact context. And so what we found, the basic result was that the average treatment effect of getting these text messages was basically increasing early filing rates from 37% to 43% in 2017, and from 38% to 50% in 2018. So those are large treatment effects. This is an inexpensive text messaging intervention. So this was a very effective policy. Something like this is, you know, you don't always get results like this, and they're precisely estimated, statistically significant. You know, you're very confident that this was a useful program. Now, in the specific case of these text messages, they're not that expensive. So in principle, you'd like to send them to everybody. But on the other hand, text messages are always sent in a broader context, and there's other things that the college might want to send people text about. So there is actually an opportunity cost of inundating people with text messages. So ideally, you would like to send these or send them more to people for whom the text messages are effective and not spam people otherwise. And then more broadly, if I was going to go design more interventions, again, I might like to understand, you know, for whom is this most effective. So, and I'm just to give the background, here's a picture of the text message content. This is kind of the sequence of messages that people might receive. There are these nudges that say, you know, do it right the first time, stop by the financial aid lab and get your help renewing. So those were some of the types of messages that people got. Now, what are we going to do with this? We're going to analyze this data after the fact. And so what we would like to do is use the data from this historical experiment and estimate using machine learning a targeted treatment assignment policy. Now, as I mentioned, and I'll show you in a minute, it may be much easier to predict who generally files financial aid than it is to predict for whom is the text message effective. And actually, you might have different hypotheses. Who's most affected? Is it the people who were most likely to apply without the messages, or are the people who are most affected the people who are most likely to forget? You know, it could be either. and maybe some other characteristics about the students, how old they are, something else could be related to the effectiveness of these text messages. So a priori, we don't really know what's going to matter, but and certainly, we don't necessarily think that the same things that are important for predicting outcomes are necessarily going to be important for predicting the treatment effect of the message. So the way we do this is we have this data-driven approach to heterogeneity. We start by estimating the conditional average treatment effect. And I have a series of papers joint with Stefan Wager and Julie Tibshirani, where we develop methods and statistical theory behind the methods for efficiently estimating conditional average treatment effects in settings like this. And we have a statistical package called a GRF in R it's got a C++ code base. And it can be potentially used in Python as well. That both targets this treatment effect heterogeneity, and it also actually accounts for potential that treatments were assigned on the basis of characteristics. In this case, that wasn't too much of a problem because it was a purely randomized experiment. We then create subgroups based on the predicted treatment effect strength to try to understand how well calibrated is our model and how good are we at actually distinguishing people with high and low treatment effects. We then compare and characterize how different those groups are. I won't show you too much about that today, but that's in our paper. And then finally, we use these Kates as what we call a nuisance parameter to choose an optimal policy. And Stefan Wager and I have a paper about efficiently estimating optimal policies using what we call doubly robust policy estimation. And then we have a statistical package called Policy Tree, which deals with the computational complexity, which is a known problem for, especially if you want to do tree-based policies, which is something that is commonly desired by practitioners. So here's the results that we have, and we broke out here 2017 on the left and 2018 on the right. And just you can focus on the simple averages in red for this talk. And so what's on the x-axis are the quartiles of the estimated treatment effects. So our model is going to basically, for every individual based on their characteristics, we're going to estimate treatment effects, and then we put them into quartiles. And we do this with cross-fitting so that the averages that are presented here are taken using data that wasn't used to determine the group assignments. So what we see here, what you ideally would have seen with a well-calibrated model and lots of data would be that, this should be all upward sloping. The fourth quartile with the highest treatment effects would indeed have high treatment effects. So each red dot is the simple average treatment effect for the people in the group. And you would want, say, the top quartile to have really high treatment effects, so that we thought they had really high treatment effects. And what you see in these pictures is that while we are able to use covariates to somewhat distinguish groups that have higher and lower treatment effects, it's not that well calibrated. So in 2017, we can sort of pick out the low treatment effect people from the rest. And in 2018, we can sort of pick out the bottom half of the treatment effect people from the top half. We're not very good at distinguishing, say, quartile 3 and quartile 4. We're bad at it, actually. And so this shows that this is a low signal environment. So even with tens of thousands of people, and we actually have a fair number of characteristics about these people, we're only moderately good at really understanding, who for whom is the treatment most effective. It's still like relatively noisy, low signal. The next exercise we do is, and this is we got a lot of information in one chart. We try to compare different types of targeted treatment assignment policies. And so the most natural one is targeting by the conditional average treatment effect, or targeting by Kate. And to understand what we do there, we've estimated this tau hat for an individual is going to be their estimated treatment effect. And if we're going to target by Kate, what that means is that we're going to prioritize most the people with the high treatment effects. And so what this picture would show for the Kate, that's going to be the olive color, is what are the benefits of, so if we compare randomly assigning, say, 10% of the people to the treatment versus assigning the best 10% of the people, how different are they? So this red line, I mean, the pink line here is what happens if you randomly assign people. So to understand the pink line, say at 25% treated, that's the benefit of randomly assigning 25% of the people to treatment. And now, since we're randomly assigning that's the line, it's linear because there's just a single treatment effect there's a single average treatment effect. And so the more people get the treatment, the better it is. But since I'm randomly selecting them, the benefit goes up linearly with the percent assigned. The olive line is showing, well, it looks a little better in terms of benefit to assign people based on their estimated treatment effects. But you also see, that's true at the bottom, like we're able to pick up some high people, but then in the middle here, there's no real benefits. We might as well assign people randomly because, we're not really getting any better outcomes from assigning people randomly than assigning them based on their estimated treatment effects. But then, if I was going to assign, say, 60 to 70% of the people, the olive line is higher than the pink, which again shows that in that region, we do get benefits if we were from using targeted treatment assignment based on Kates. Now, the next ones, we call them baseline and inverse baseline. Those are really predictive models. So those are models that you could do using historical data. And this you wouldn't need an experiment to figure out these. And these are just basic, simple predictive models, not models that are targeted for causal inference. So in particular, the baseline, the first hypothesis might be, let's predict people who were not going to fill out the financial aid form anyway. And the intuition for that is, well, gosh, if people were already going to fill out the financial aid form, then what good does a text message do? There wouldn't have any effect. So finding people who weren't going to fill out the financial aid form anyway, that seems like a good group to try to target for intervention. But it turns out, if you look at this red line, it's substantially worse than average. And actually, that's a terrible group to target in this environment. And that's, I think, afterwards, we look at the data and the covariates associated with that group. And these are basically people who maybe are also very likely to drop out of college. And so what we are finding is that in the data, we can actually more accurately predict people who are just not going to do this, whatever you do. No text message is going to get you to apply to financial aid form. But we didn't know that ahead of time. That came out of the data. Now, in the bright blue is the inverse baseline. That is targeting people who say they will fill out financial aid forms. And these are people who just need a small nudge to get over the finish line. And so it turns out that targeting policy actually does, for the most part, even better than the policy optimized for causal effects. Now, that's surprising because we were optimizing for causal effects. And that shows that in a low signal environment, if you can actually confuse yourself by targeting treatment effects. And of course, you wouldn't have known that this was going to be the best, but it turned out that this was actually the best thing to do. And that's an example where you really need more data to do this well. So overall, that this is kind of showing, in this case, I set out, actually, I was hoping to show, oh, it's great that targeting for causal inference is always the best thing, but we end up with like a mixed result. Certainly you need to think about this issue, but in a low signal environment, it may be too noisy to really estimate treatment effects super well. But it also highlights that, I could have guessed wrong. I could have used a predictive model and guessed that would be good for targeting and been wrong. So thinking about it in terms of causal effects is very important. All right, let me move on to a second example. In this case, we're personalizing stories in an educational application. And this is joint with Ayush Kanodia, who's a CS PhD student at Stanford, and ML Pellico, who's a postdoc with me. And here we're analyzing a small but growing educational technology application called Freedom in India, where kids aged 3 to 12 learn to read English. The app recommends stories to read, and it's a startup. And so right now or in the time period we studied, they had 2,000 to 4,000 daily users reading 1 to 2 stories per session. Some of the questions we wanted to ask here was sort of like man versus machine. Can personalizing recommended stories improve student engagement over human selected stories? So humans might pick out stories they think people are going to like, but they're giving the same story to everybody, while the personalization engine is going to just be data driven, but it's going to be able to target stories to students. A sub question is, well, with such a small sample, are we able to improve upon the human approach? Is this enough data to do it? And do recommendations work for more frequent users or for more common stories, which will start to hint at the value of growing the app for the quality of recommendations, as well as the value of retaining data about users. So there's actually a couple different segments here. This isn't too important what the segments are, but there are paid users, business to consumer users, and business to business users. And there's a bit of a funnel for the students as they go through. You're going to show them a story. First they have to view the story and see if, read a little more, see if they like it. Then they could start reading the story, and then they could complete the story. And so what we're going to do is evaluate this in terms of a ad hoc utility that we came up with the app about putting the most value on completing a story, but intermediate values on other parts of the funnel. And we see that the red or the yes from all 3 channels, we do see a big fraction, about half, finishing stories, but you are losing people at different parts of the funnel as well. So what we're going to do is we're going to run a randomized experiment where the treatment group sees stories from a recommendation system, while the control group sees editor selected stories. And we're going to use a simple collaborative filtering model, partly because we don't have that much data. Before the experiment, we tried a couple of different recommendation systems. We did offline off-policy evaluation of popularity-based recommender. And actually, I didn't write it here, but we also looked at using observable characteristics of stories. And the winner was collaborative filtering. And we found that it worked better for common users or frequent users, as well as common stories. And so our accuracy fell off if we didn't have enough data. Then in the experiment, we had we did the experiment on 3,000 users who launched the app over a 3-week period. And we stratified the experiment to reduce the variance and ensure covariate balance by activity, grade level, and the type of user. So we designed and powered the experiment for our primary metric, which was total utility. And indeed, the experiment was just long enough to pick up our hypothesized effect sizes. So and again, even data is important for building recommendation systems. It's also important for evaluating recommendation systems. So here we actually had a 33% gain in our utility, but in this 3-week experiment, we just barely can detect that treatment effect. So the average treatment effect is 0.15 in terms of this unit of total utility. Again, that's a 33% gain, but the standard error is 0.07. And so we planned the experiment. We were expecting a really big gain, but we needed 3 weeks even to detect that big a gain with such a small user base. All of our supplementary metrics are supportive in moving in the right direction, but actually they're not statistically significant at the 5% level. But we see utility per day goes up. It seems like most of what's happening is that people are getting higher utility within the sessions they have, but there's also a modest 6% increase in the number of sessions. So people who have a good experience are more likely to come back, but we'll need studying questions like that often takes more data. And honestly, that was also my experience in working with a search engine historically, that trying to estimate the impact of quality on whether users come back more frequently it's pretty noisy, and you often need a lot of data to estimate that. Then we try to look at the value of data in terms of the users. type. And so this is a graph where on the x-axis, we've ranked the percentile of the user in terms of how much utility they had generated in the past, basically how many stories they read in the past, but weighted by start views and completions and so on. And the bottom chart is basically the same thing, but we've just done a simple count of the number of stories they read in the past. And so for both of these metrics, what we see is that the treatment effect is higher for the higher users. So on the y-axis, actually, we have the AIPW score, which is a kind of covariate adjusted treatment effect, but just think of it as a treatment effect. And so what we see is that there are, positive treatment effects for all parts of the distribution, but the treatment effects are larger for the more frequent users. Now, you can immediately think about this and see, well, I can't distinguish whether just the more frequent users happen to like the kinds of stories recommended by our recommendation system, or whether we had better statistical accuracy with the more frequent users and the less frequent users, because all we've got is frequency of users. They might be different from the infrequent users in some other ways. So we don't have a clean value of data interpretation, but we do see this suggestive evidence that we're doing a better job. This recommendation system gives more uplift for the more frequent users. And then just breaking that down into something simpler, we look at the people above the 75th percentile versus the people below the 75th percentile in terms of utilization. And we see that we can distinguish those two. And again, there's a substantially higher impact for the above 25%. We also look out and see, how does this look in the story distribution? And the way we do this is that we we create percentiles in the story distribution, where we look at the 1% of stories that account for, we look at the set of stories that account for 1% of recommended stories in the treatment group and in the control group. So, there might be a different number of stories in the treatment group than the control group as well. And indeed, there are some differences there. But what we overall see is that the control group, which got the human recommended stories, does better for the top 1% of views. So the most common stories that accounted for 1% of views, the human stories are good. They're better than our recommendation system. But all the way throughout the whole rest of the distribution, the automated recommendation system does better. So basically, the humans are able to pick a few winners, but they're not able to match users to stories successfully throughout the distribution. And so this is kind of exciting, because even in the small application, the machine is beating the human selected and curated stories. Okay, so the last application, I'll go left. Didn't leave myself quite enough time, so I'll go a little bit quickly. But we're looking at the value of data for price targeting. And this is building on some work that I did with David Bly at Columbia and Fran Ruiz, who at the time was a postdoc at Columbia, and my student Rob Donnelly from Stanford, and then some in-progress work with some combinations of those co-authors as well. And what we're looking at are ways to estimate targeted treatment assignment policies for coupons. And here, the prediction versus causal inference problem, again, is that it's easy enough to predict who buys in general, but we want to know how people respond to changes in prices. And so that's actually more of a parameter estimation problem than it is a pure prediction problem. And again, we need to know that we had variation in prices in the past, and we need to have seen people buying products with different prices. In this case, we do not have a randomized experiment. We're using observational data. And so the way that we're learning about the impact of price changes is we're comparing similar people who came to the store just before and just after a price change. And then our goal here in the most recent paper is to estimate the value of different types of data about retention, like how long of a user history do I have, more product categories, more users, to try to understand in an e-commerce application, what is the value of data. And again, we're going to want to kind of break apart what is the value from enriching your model versus just adding more data to an existing model. So the general framework for shopping that is used in economics and marketing is based on multinomial logistic regressions and their generalizations. And back in the early 1970s, again, data science was invented before, the year 2000 and definitely before the year 2010. We've been doing data science and economics and marketing for a long time. Dan McFadden won the Nobel Prize for his work connecting utility maximization to variations on logistic regression models. And so the basic idea is that if a user is maximizing utility and choosing the product from a set that maximizes their utility, and the idiosyncratic component of the user's preferences is distributed type 1 extreme value or gumbel, basically, logistic errors, then the probability that user U at time t purchases item I has the functional form from a multinomial logistic regression. And so how is that useful? Well, if I estimate the parameters of the logistic regression, I can interpret them as parameters of the user's utility function. And so I express the mean utility as each user U has a utility for item I minus some user-specific parameter that that determines how they feel about prices. And rich users might care less about high prices, and poor users might care more about high prices, for example. So if you observe consumers over time and the prices vary over time, in principle, you can estimate a consumer's price sensitivity. And that's going to be our goal, is to estimate this parameter, which is a coefficient on the price. And we do it in such a way to try to isolate the effect of changes in price. Again, it could be that there's a holiday and, something's got high prices and people want it a lot. So we need to avoid that type of variation in price and focus on kind of more local price changes within a period. And we drop holidays and do all sorts of other things to help with that. And we have a bunch of sensitivity analysis to validate that. So traditionally in economics and marketing, people would study one category at a time. So, I've supervised, an entire thesis about laundry detergent, like another one about paper towels. And you would spend a lot of time trying to estimate price sensitivities in those categories. And then you would use it to answer questions like what would happen if two companies merged. And the nice thing about this utility maximization approach is it tells you if you take a product away or if you add a product, how will people redistribute their purchases? The logit functional form will tell you what consumers would do in counterfactual scenarios. It also tells you what would happen if you change price, and you can use that to talk about consumer welfare. So that's this whole literature in economics and marketing. To bring in machine learning, we maintained the utility maximization approach, but we study many categories in parallel, and then we use matrix factorization, or in some cases neural nets, for this user item coefficient here. One of the other things that Dan McFadden did for this Nobel Prize winning work is he recognized that in many cases, the multinomial logit model gave very misleading counterfactual predictions. And part of that was because there's often correlation in preferences among groups of products. And the most important correlation is just, do you buy the product or not? Whether you buy it is among products is all, your utilities are all correlated, because there might just be one day where you just don't want the product at all. So there's something called the nested logit, and there's this nice functional form for what's called the inclusive value, which is basically this log of the sum of e to these mean utilities, and that allows you to connect your preferences about prices that are estimated in a model conditional on purchasing. So we estimate what would you buy conditional on purchasing. We learn about price sensitivities, then we plug that in using this functional form, and then we have a second stage model that says, do you buy or not? Now, in principle, you can estimate this all jointly. And one thing that has made this whole project slow down is that initially we faced a lot of computational problems with trying to estimate this whole system jointly. And recently we've now, after many months of tinkering with it, we've now got a new package that allows us to do this much faster. And as I'll show you, we do a lot of tuning and retuning to do our project here. I should say that's sort of interesting from the intellectual history. Way back in the early 70s, people would do this in a two-stage way because they didn't have enough RAM, and then all these software packages were programmed up that could do this on medium-sized data sets. Now we're back in a world with big data sets and very complex machine learning models. And so again, we did it the two-stage versus joint optimization became an issue, just like it was in the early 70s. We do this with variational Bayes, and we have a bunch of computational tricks to deal with the nonlinearities, because just going back to these equations here, we're going to have latent parameters in the denominator, which makes the computation harder. So just to look at finally what's our value of additional data strategy, what we do is we take 4 stores, we take 200 product categories with 1,800 items, we take 6,000 users who are frequent enough users of these stores, and 600 days. Then we take a representative subsample with 100 product categories, 2,000 users, and 350 days. And we make a fixed base test set. And then our strategy is to keep expanding the data set size in different dimensions, re-estimating the model, and then see how we do on the same base test set. And then finally, we retune the model at each endpoint to see, to decompose basically the value of data for a fixed model versus the value of data for allowing you to estimate a richer model. Now, as I mentioned, we ran into a lot of problems with tuning and retuning and computation. So these are actually kind of old results, and we're just in process of having lots of machines go and redo all of this at a much larger scale. So these are just from one run, so super noisy. So apologies for that. But you can kind of get the idea here that what we show is, first of all, for goodness of fit, as you increase the number of days that I have per user, the goodness of fit goes up pretty steeply. But then this last big spike is what happens if you retune the model, and we get a much bigger lift from retuning models than we do from just adding data to models of a particular complexity. In this case, we found adding different product categories, so seeing the consumer purchase lots of different categories, didn't have a lot of value until you retuned the model. And somewhat similarly, adding more different users. So in this case, just getting more user retention, seeing individual users for longer, was the most important value of data. So I'm just running out of time. We do a lot of effort with off-policy evaluation and validation of our counterfactuals in the paper. So just the conclusions on that part were that we learn parameters of consumers' utility through revealed preference. And then we predict counterfactual responses to alternative situations. And we had to find a data set that had enough price changes in it to assess consumers' responses to price changes, but things are still pretty noisy. And then we evaluate the value of personalized targeting and how it varies with alternative data set sizes. And some things we've learned across all of these projects, not all data is created equal. And not all types of data are created equal. But in many of our cases, being able to observe users over a longer period of time did seem important, at least at the scales of data we were looking at for making recommendation systems. And also enriching the model seemed more important than just adding more data to a fixed model in the supermarket case. So let me stop there, and happy to take questions. I'm not seeing anything in the Q&A, I think.
Okay, thank you very much, Susan. It's been a really nice talk. And there is no question in the Q&A, and I don't know if the participants, they want to do any question. Meanwhile, I would like to ask a question that probably is trivial. It's a general question. Basically, your talk is about the value of data for personalization. And of course, one thinks about health. What is the value of data for personalization in health? I don't know, you have any experience, or you can tell us something about that, because it's really on fashion, this personalized medicine, and I don't know if it really makes sense.
Sure. Yeah, that's a great question. And health actually faces a lot of these problems. I did a whole project during COVID about trying to understand the causal effect of something called alpha blockers, which a lot of older men take for prostate conditions. And it turned out that that seemed to have preventative effects against pneumonia and ARDS and also COVID. So in studying that, so that's forget about the personalization, just like, hey, you have this really important health problem, especially early in the pandemic, how do we find ways to treat people using medical data? And a huge problem there is that, we didn't have enough randomized controlled trials. So just using that as a case study, the way my team approached this, we had some mouse models that suggested that these drugs would be good. So this wasn't just completely out of the blue, but it hadn't been studied in humans. So we went back to old data, and particularly for the case of alpha blockers, we had a situation where the people were taking alpha blockers, but not because they had COVID or not because they had pneumonia. They were taking alpha blockers because they had problems peeing at night. So that's not related to your respiratory system, although it is related to your age. So we spent a lot of time just trying to figure out how to use observational data carefully in order to draw suggestive causal conclusions about the impact of being on alpha blockers at the time that you contracted pneumonia. So we had to study very similar men, and we used these techniques from causal inference to come up with convincing estimates. And we actually replicated it in like 5 or 6 countries, and we used that to promote a clinical trial. But even in those cases, we had like 10 years of data about everyone who had pneumonia in like several countries, or a big chunk of the U.S. And we had a lot of older men are taking these alpha blockers. So we had a pretty commonly prescribed drug. And even there, our confidence intervals for even just saying that this drug works on average were pretty wide. So then to try to break it out and understand the treatment effect heterogeneity, like that's my main interest. And we found a little bit of evidence there, but things were really just too noisy to do that, especially once we had to take account of the fact we didn't have a randomized controlled trial. And then if we wanted to run a randomized controlled trial, those are often having like a couple hundred patients at most. So again, we're often don't have enough statistical power for treatment effect heterogeneity. So in that sort of case, what we would need to try to do is get funding agencies to fund larger randomized controlled trials. But it's still going to be really difficult. So in that kind of environment where it's really hard to draw causal inference, conclusions from observational data, people in personalized medicine, a lot of times you do follow this sort of 2-step approach where you build a predictive model, that's sort of trying to figure out just for whom do we think this might work, or for whom are they likely to have complications? You're predicting pieces of the puzzle. But then ultimately you need to do RCTs, randomized controlled trials, to really understand whether your predictive models are right in terms of their prioritization. One other challenge that we have in medicine is that the journals, really don't know how to evaluate causal claims from observational data. So a lot of the top medical journals, you can either publish correlations or prediction models, or you can do randomized controlled trials. But they're not very good at saying, well, here's some evidence that's not from a randomized controlled trial, but it might have some implications for who should get what drug. And I'm just to finish this little tirade, sorry, but like if you think about what typically happens with a drug is that, you might do a randomized controlled trial with a couple hundred people, and then it's prescribed for 20 years. So there would be a lot of potential data afterwards that could be used to help figure out for whom does it work and why. But the whole system is not set up to continue the surveillance, to continue randomized controlled trials afterwards, to publish the evidence and to translate it to practitioners. So I think a lot of the problems we have in not fulfilling the potential are that it's not just the statistics, it's like the whole infrastructure and the community aren't set up to produce and receive this kind of information to reach its full potential.
Okay, thank you very much, Susan. I don't know if there are more questions. There is no question and answer in the chat, and I cannot see any raised hand. I think that most of us, we are European, and probably we are quite tired after the whole day of conference. And I think because no one wants to ask a question, I would like to take the opportunity to ask another question. So I can imagine that you have worked with many companies and you can carry out many studies. And has it ever happened that you told a company, okay, don't continue gathering data because your data has no value for personalization or for the goal that you are looking for?
Sure. Well, most of the major companies don't, even without the privacy regulation, frankly, it's just too expensive to keep everything. So if you think about like a social media platform, when you scroll through stuff, like if you tried to capture everything that a person saw scrolling all day, it just gets too big. And even for like the largest e-commerce companies, trying to build a model that takes into account everything that somebody saw is too much. So if you think about building a recommendation system, a lot of times the data that you get is, well, this person watched this movie or this person bought this product. But of course, if you really want to understand their preferences, you'd like to know, what did you see on the screen when you chose that choice? I mean, that's much more important, actually, and you can learn a lot more about your preferences if you have that. But generally, these firms have not really kept all of that data. The search engines keep the page views, but the other places often don't really keep track of what you actually saw on a given day because the data gets too big. Now, I actually think that data does have value, but of course, it's also very expensive. So, it's a cost benefit. And then, keeping how long you keep raw data, like you can sometimes get into these chicken and egg problems where people say, hey, is anybody using this data? And it's like, no, we never go back in time. And then you delete it and you say, well, actually, did you realize if I wanted to do seasonality and holidays, like I need 3 or 4 years of data. And if you keep deleting it, we'll never know whether seasonality prediction works or not because we never kept the data long enough. So in environments where it's super expensive to keep data, you can see, data getting thrown away for these various reasons. So it's actually really hard for companies to figure out when you might think, oh, all these companies have great ways to value data. But, it's hard because like, what would happen if counterfactually I had twice as much data as I do? Well, I might build a whole model, but like I would spend 6 months engineering it. And like, I don't know what that would be. And then you could say, well, what would happen if I had half the data I have now? Well, you can try to retrain your models on less data, but you had the bigger data set when you made a lot of choices about what a good model was. So that's not necessarily going to say like next year when all the information is stale, will I still be able to build good models with half the data? So trying to do these counterfactuals of like, data that I haven't had before, they require such complementary investments and time that it's actually pretty difficult to know what the value of data is.
Okay, thank you very much, Susan. So if there is no more question of hands raised, I think we can stop here and thank you again for this nice talk and really interesting talk. And hope you come to Bilbao and to know the city next time. Okay.
Thank you. Well, thanks so much for sharing and for asking the great questions. And hopefully we'll meet again. Thank you.
Okay, bye.
Bye.